Okay, so the first example that we're going to take a look at is adding and subtracting. So let's say that we have a few different values and we want to figure out what's happening. So let's say that we have length values that we're adding up. So let's establish what these values are. Let's say W is 4.52 plus or minus 0.02 centimeters. Let's say that we have our value y is 3.0, not quite as precise, plus or minus 0.6 centimeters. Then we have our value of x. Let's say x is 2.0 plus or minus 0.2 centimeters. So we have three values, and let's say that this is what we want to do with it. Let's say z is the value that we want, and we're going to take x, add it to y, and subtract w. Okay, so what we're going to do when we add or subtract is to get those values is we basically add the uncertainties together. So the uncertainty in z is equal to the uncertainty of x plus the uncertainty of y plus the uncertainty of w. So when we calculate this out just normally, which we can do here, we'll take z is going to be equal to x, which is 2.0, plus y, which is 3, and minus w, which is 4.52. We're going to get a value of, let's see, 0.48. Okay, now we've got that value, but how precise is it? It's plus or minus what? Is it 0.48? Could it be, how much higher, how much lower could it be based on our measurements? So what we do for our uncertainties, we say, okay, the uncertainty in x here is 0.2, plus the uncertainty in y is 0.6, and the uncertainty in w is 0.02. So when we add those up together, that's 0.82. And if we round to 1 sig fig, that would be 0.8. And so that's our uncertainty. So it's interesting here. We have our value of 0.48, which we'll round to 0.5 to keep 1 sig fig. 0.5 plus or minus 0.8. So this is quite uncertain. Like this value could be much, much higher, much, much lower. That's because we're so imprecise here. If you look at y, right? Y could be as high as 3.6, as low as 2.4. Here with x, it could be as high as 2.2, as low as 1.8. And even though w is pretty precise here, we're in trouble with these other two. And so we have our uncertainty there. Okay, let's take an example of multiplication. So let's say that we have two values here. Let's say we have a value of w, which is 4.52 plus or minus 0.02 centimeters. And let's say that we have a value of x, and that value is 2.0 plus or minus 0.2 centimeters. And let's say that we want to get the area, and the area is going to be w times z, or w times x rather. And so what we do with this is we use an equation of, and this is you don't have to memorize this. This is on your IB equation sheet. The uncertainty in z over z is going to be the uncertainty in w over w plus the uncertainty of x over x. And how we get about this, we're going to gloss over a little bit here. When you take statistics, this will, you'll see how we get this, as we take a look at standard deviations and that kind of thing. And so, yeah, what we want in this case, w times x, if we actually just calculate that, that's going to be, 4.52 times 2. And in that case there, we get 9.04. But, and that's centimeters cubed, right? But how precise is that? It's plus or minus what? How much bigger, how much smaller can it be? And that's where we're going to need this. Okay, so let's do that. We're going to take these values, figure out how we get that. So the uncertainty in z is what we want over z, so that's 9.04. That's what we just did right here when we calculated that, is equal to the uncertainty in w, which is 0.02 over what w is, 4.52, plus the uncertainty in x, which is 0.2 over what x is, which is 2. And then our next step will be actually calculating that out. So 0.02 divided by 4.52 is 0.004425. You could keep the value in your calculator, and then you're going to add that to 0.2 divided by 2. So 0.1 plus 0.1. And so we end up getting 0.104425 is the uncertainty of z over 9.04. And so when we put this over 1, we'll cross multiply, and uncertainty of z comes out to be we multiply that by 9.04. We get 0.944. And yeah, and so what we do, again, we'll round to one significant figure, so to 0.9. And that's what we've got. So in this case here, the final answer would be we're 9.0. So again, going back to our rules here with the number of significant figures here, we have 2. 9.0 plus or minus 0.9 centimeters squared, which is much better, because now we know that it's either it could be all the way as big as 9.9 or as small as 8.1, and so this means a whole lot more. Okay, now with division, it's similar to multiplication. Let's say that we have a couple values here. Let's say we have a value of x of 2.0 plus or minus 0.2 centimeters. And let's say we have a value of y, which is 3.0 plus or minus 0.6 centimeters. And we want to divide the two. And so z is going to be equal to x over y, x divided by y. And we want to get that and how certain we are and get the uncertainties with it. So what we'll do is we'll take x 2.0 over 3, and that'll be 2/3, which is 0.67 repeating, and plus or minus what, right? So in this case it's going to be unitless because we have centimeters over centimeters, so those centimeters cancel out. Centimeters over centimeters, those cancel out, and so plus or minus some value, right? So it's 0.67 plus or minus some value, and so the equation is actually the same for dividing and multiplying. The uncertainty in z over z is equal to the uncertainty in x over x in this case, plus the uncertainty of y over y. And that will enable us to get what this is. So let's go ahead and do that. And I'll just pull this over here. Okay, so the uncertainty in z over z, z is 0.67 repeating, is equal to the uncertainty in x, which is 0.2, over x, which is 2, plus the uncertainty of y, which is 0.6, over y, which is 3. So we can work these out. So 0.2 over 2 plus, which is 0.1, plus 0.6 over 3 and that's 0.2, so 0.3, and so we have the uncertainty in z over 0.67, or 2/3, so it'd be better to do that way. So so the uncertainty in z, that times 2/3 will give us 0.2. So 0.2. So what this is then, it's much more helpful. It's 0.67 or 2/3 plus or minus 0.2. So it could be 0.2 higher or 0.2 lower. And again, that's very, very helpful because without that, we just don't know how good that value is. All right, so let's say that we have an exact value. Let's say that we have a circle and we've measured the radius of the circle, and let's say the radius is equal to 3.0 plus or minus 0.2 centimeters, and we want to find out the circumference. Well, circumference is 2 pi r, so that's pretty easy. 2 pi times 3, and we get 6 pi. And 6 pi is 18.85. And, rounding to, the uncertainty, we can do that as well. So, that would be centimeters squared. No, just plain centimeters, right? How far it is, so just centimeters. Okay, so what we do with uncertainty here, the uncertainty in their circumference, the way we do that is we multiply the constants, 2 times pi times the uncertainty in the radius. And so we just do that. So 2 times pi times 0.2 is going to give us 2 times pi times 0.2, 1.25. Okay, and we'll round to two significant figures here, so 1.3. And so, yeah, if we look at that, now we have something a lot more useful, 18.9 plus or minus 1.3 centimeters. So that's helpful because, we're uncertain by 2 centimeters here. So therefore, when we calculate the circumference, we're saying that it's 18.9, but it could be, 1.3 higher or 1.3 lower than that based on our uncertainty there. All right, so now let's take a look at an example where we have kind of a combination of some things. If we're looking at just a basic powers example, let's say, z is equal to x squared, and let's say x is 2.5 plus or minus 0.3 centimeters. What we do with that is we'll come here, it's really just x times x, right? So, we looked at this before where, we have the uncertainty in z over z would be the uncertainty of x over x plus the uncertainty of x over x again, right? Because what this really is this x is times x, and we're using the multiplication rule here. So we would have, the uncertainty in z over z, in this case 2.5 times 2.5 is 6.25, so 6.25 is equal to the uncertainty of x, which is 0.3 over 2.5 plus the uncertainty of 0.3 over 2.5. And if we do that, really what this is, right, is just 2 times 0.3 over 2.5, right? So the rule is with powers is you have the uncertainty in z over z is equal to how many powers you have. So in this case, we have 2, but you could have more than that. And then you have the uncertainty of x over x. And so let's actually change this to the integer and integer, whatever this is, right? So whatever the exponent is. And so let's go ahead and do a worked example where we have this as well as the other values here. So let's say that we have a few things here. Let's say W is 4.52 plus or minus 0.02 centimeters. Say we have a value of A, which is 2.0 plus or minus 0.2 centimeters squared. And let's say we have a value of Y, which is 3.0 plus or minus 0.6 centimeters. And let's say Z is equal to, and that's our goal, is W times Y squared divided by the square root of A. Okay, so we're doing a couple things here. We're multiplying W by Y squared, and then we're dividing this by A. So in this case here, to get uncertainty, it'd be the uncertainty of Z over Z. You know, we're multiplying W by Y squared, so we can have the uncertainty in W over W plus, now in this case here, we're squaring Y, right? So just like we said before, we're going to have the integer N, the absolute value of that, of Y over Y. And then we have the square root of A, so that's an integer, and we'll look at that as well, of the uncertainty of A over A. So let's actually put the values in here. So when we calculate this, we have the 4.52 times 3 squared over the square root of 2. Okay, and so when we do that, let me do that real quick. 4.52 times 3 squared divided by the square root of 2, we'll get 28.77. Okay, 28.77, and we're limited by the number of sig figs here, which would be 2, so this would round to 29. Okay, so when we place these values in here, and I'll put that in red here, so we have the uncertainty in Z over Z, and in this case 29, but we'll use the raw value starting out, so 28.77. The uncertainty in W is 0.02 over 4.52. Now, the integer here is squared, so we're going to have 2 times the uncertainty in Y, which is 0.6 divided by Y itself, which is 3, plus, now the integer here, this is taking the square root, which is A to the 1/2 power, right? So what we do is for the integer, it's going to be 0.5 times the uncertainty of A, which is 0.2 over 2. Okay? So, and that'll give us the uncertainty in Z. So let's calculate the right-hand side. And I'm going to put this all on my calculator. 0.02 divided by 4.52 plus 2 times parentheses 0.6 over 3 plus 0.5 times parentheses 0.2 over 2, and we'll get 0.4544 is equal to the uncertainty of Z over 28.77. So the uncertainty of Z to 28.77 is going to be 13. So our uncertainty is plus or minus 13 from this. So what we're saying is it's plus or minus 29 plus or minus 13. And that's helpful because we can know that, you know, it's going to be higher or lower by that amount, and that makes it a lot more useful for us. All right, so now let's take a look at a combination of a couple different things. Let's say we have a measurement of W, which is 4.52 plus or minus 0.02 centimeters, and we have a value of X, 2.0 plus or minus 0.2 centimeters, and we have a value of Y, 3.0 plus or minus 0.6 centimeters. And let's say that Z is equal to W times X plus Y squared. So I'm actually going to have you try this one to get what the what value of Z is, plus or minus what it should be. And so you're going to calculate the uncertainties and then add up the uncertainties, and we'll see if you can do that. So go ahead and pause the clip and give that a try, and when you're ready to check, you can hit play to continue. All right, so let's see how you did. The first thing that we'll go ahead and concentrate on here is the W times X. So to get that, we've got the multiplication rule. So we got to bring those and figure out what that is. So the uncertainty of Wx we can find by this, the uncertainty of W over W plus the uncertainty of X over X. And then that will give us the uncertainty of Wx, which we're going to need first. So we've got that uncertainty Wx over, so W times X, 2 times 4.52 is 9.04. So 9.04 is equal to the uncertainty of W, which is 0.02, over W, which is 4.52, plus the uncertainty of X, which is 0.2, over X, which is 2. So we'll do that. So 0.02 over 4.52 plus 0.2 over 2. And we'll multiply that by 9. Well, I'll write that down so we got that step. So 0.1044 uncertainty of Wx over 9.04. So the uncertainty of Wx, 9.04, so 0.944, okay, is the uncertainty of Wx. So that's going to be critical. Now what we can do is we can take a look at the uncertainty of Y squared. So we have the uncertainty of Y squared over Y squared. Oops. Over Y squared is equal to the integer n of the uncertainty Y over Y. So in this case here, the uncertainty Y squared over what is Y squared, which is 9, is equal to the integer 2, because this is being squared. So 2 times the uncertainty in Y, which is 0.6, over Y, which is 3. And so we'll do that, 0.6 over 3 times 2, which is 0.4. So 0.4 uncertainty Y squared over 9. So the uncertainty in Y squared, is 3.6. Okay. And so now what we can do is bring these together, because now we have Z. We know Z is equal to Wx plus Y squared. And we actually have those values. So remember, when we add, we just add uncertainties up. So in this case, the uncertainty in Z is going to be the uncertainty in Wx plus the uncertainty of Y squared. So we can do that. We've got the uncertainty in Wx, which is 0.944, plus the uncertainty in y squared, which is 3.6. So that'll give us 4.544. Okay. And in this case here, 2 sig figs, so 4.5. And then if we look at z, we can actually calculate z now. We take w, which is 4.52, times x, which is 2, so 9.04, plus y squared, which is 9, so 18.04, 2 sig figs is 18. So we have 18 plus or minus 4.5, and so that is our uncertainty for this value where we brought it all together here.